of f. So if z equal to f of xy, we use the following notations. Fxx means already we have obtained first order partial derivative fx, and we differentiate the expression fx with respect to x again. That will be denoted by fxx or f11 or del by del x of del f by del x. That is also denoted by del square f by del x square, or the function is z equal to f of xy, therefore del square z by del x square. Similarly for the partial derivative of fx with respect to y, so that will be fxy or f12 or del by del y of del f by del x, and that is equal to del square f by del y del x. Generally, if we consider continuous functions, then the expressions del square f by del y del x and del square f by del x del y are the same. Okay, so that is f12 will be f21 in case of continuous functions, the functions which are continuous and which have their first order partial derivatives continuous. And similar, this is notation for fyy, that is second order partial derivative of f with respect to y. So as the number of independent variable increases, this number of partial derivatives will increase. For example, if you have 3 independent variables, then you will have 3 first order partial derivatives, and so total fx, fy, fz, then fx, yz, fxx, x, fxx, z, fxx, y, and so on. So the number of partial derivative increases as the number of independent variable increases. Now partial differential equations, the topic of this lecture. I feel to discuss the previous slides first. Now we go to partial differential equations. Partial differential equations is an equation containing an unknown function of 2 or more variables and its partial derivatives. So this is similar to the definition of ordinary differential equation. What was there? The ordinary differential equation means an equation that contains the dependent variable, the only single independent variable, and the derivatives of the dependent variable with respect to the independent variable. Here in case of partial derivative, we have function of more than one variables, and therefore partial derivatives of the dependent variable with respect to the independent variables, dependent variable and independent variable involving a function, all these, it is called a partial differential equation. The invention of partial differential equations by Newton and Leibniz in 17th century marked the beginning of modern sciences. PDEs arise in the physical problems, both in classical physics and quantum mechanics. Orbits of planets or spaceships, flow of the liquid around a submarine or air around an aeroplane, electrical currents in the circuit or processor, and actually majority of the physics and engineering inspired problems are described by partial differential equations. Now PDEs in some important and very well known partial differential equations in science and engineering are, you might have heard their names or read in some books. First is Laplace's equation. Generally these arises in gravitational or electrostatic potential, and you can consider Laplace's equation for 2 variables, 3 variables, 4 variables. Here it is written for 3 variables x, y, z. It is nothing but uxx plus uyy plus uzz equal to 0. That is del square u by del x square plus del square u by del y square plus del square u by del z square equal to 0, where u is considered as a function of 3 independent variables x, y, and z. So this is the Cartesian form of Laplace's equation. Second is heat equation. It is del u by del t is equal to a square. So I think there is some problem with the equation in this font, with this font pattern. Next is wave equation, and next is Schrödinger equation. Schrödinger equation comes in quantum mechanics and electron probability densities. Next is Navier-Stokes equation, fluid flow, fluid velocity, and pressure. So Navier-Stokes equations are very important in the problems containing fluid dynamics or fluid flow. Next is differential operators. So before we go to partial differential equations, using the partial derivatives, differential operator del by del x or del by del y del by del z, using the first order partial derivatives, differential operator del is introduced here. In the differential equations, there are several derivatives that occur very often. For example, the vector of first derivatives of, or also known as gradient of the function. So it is denoted by grade f, where f is a scalar function of three independent variables x, y, z considered here. A scalar function means a function f of let us consider three independent variables x, y, z. So a function of three independent variables x, y, z, it is a scalar function if it assigns a scalar for each x, y, z belongs to R3. So at each point of the space, if a function f, x, y, z assigns some scalar that may be related to some physical potential or some physical quantity, that is called a scalar function. So the gradient, the grade, that is del, it is defined as del by del x, comma del by del y, comma del by del z, and when it is operated on this scalar function f, it gives gradient of f. It is del f by del x, comma del f by del y, comma del f by del z, and the result of a scalar function is a vector function actually here, because del f by del x, you can consider this expression also with the ijk, that is del f by del x into I plus del f by del y into j plus del f by del z into k. To clarify the notation of PDEs and facilitate the calculations, the notation of differential operators was invented. Thus, nabla or grade stands for gradient, and it is defined by del x, del by del y, del by del z. The sum of second derivatives of f of x, y, z formally obtained as the scalar product of two gradients. Two gradient operators is called a Laplacian, that is grade dot grade. Grade dot grade, that is dot product of two vector differential operators, nabla dot nabla gives you del by del x, comma del by del y, comma del by del z dot del by del x, comma del by del y, comma del by del z, that is del square by del x square plus del square by del y square plus del square by del z square, and this is also denoted by delta, capital delta, or nabla square, and this is called Laplacian or Laplace operator in Cartesian coordinates. Next, we define the divergence of a vector function. So if we have a vector point function f1 x comma y comma z, that is f1, f2 and f3 here are functions of the space coordinates x, y and z. Okay, so a vector function means like scalar function. Scalar function assigns a scalar to each point of the space x, y, z are of R3. Similarly, a vector point function assigns a vector at every point of the space. For example, if you consider the vector point function x square I plus y square j plus z, x, y, z, k, then at point 1, 1, 1, it is the vector I plus j plus k. Okay, so the divergence is defined for a vector point function, and it is the sum of its first derivatives or scalar product of the function with nabla. So the given vector point function and its dot product with nabla is the divergence of that vector point function, and it is a scalar value. It will give you a scalar value at each point of the space. So divergence of f is del dot f, that is del f1, f has coordinates, f has its components along x, y, z directions f1, f2, f3. These f1, f2, f3 may be functions of x, y, z. Then del dot f is del f1 by del x plus del f2 by del y plus del f3 by del z. Now the rotor of a vector function. So rotor or curl, it is also known as curl. The rotor of a vector function f1, f2, f3, where f1, f2, f3 are functions of x, y, z, is the vector product of the function with nabla. So del operated on a scalar point function was gradient. Del having its dot product with a vector point function f having components f1, f2, f3, that is called divergence. and the curl is nothing but the cross product of del, that is the operator del by del x plus del by del xi plus del by del yj plus del by del zk, with some vector point function having components f1, f2, f3, that is f1i plus f2j plus f3k, you can say it is the cross product of del and f. So cross product of del and f, it is called rot f or curl f, and it gives rotation. And if this determinant is 0, the vector point function is also said to be irrotational. So it is defined by this determinant. First row is ijk, the unit vectors along x, y, z direction. Second row is consisting of the components of the nebula, and the third row is consisting of the components of the vector point function, that is f1, f2, f3, and the result of curl of a function will be a vector point function. Okay, so other coordinate systems. Now in other coordinate systems, let us see what is the form of at least one equation, say Laplace's equation. We define the differential operators in Euclidean coordinates, right? However, it is sometimes more convenient to use other systems like spherical coordinates r theta phi, r theta nu, or spherical symmetric problems where rho phi z for cylindrical symmetrical problems. So this is the first case. In cylindrical coordinates, a point in the space having coordinates x, y, z that has its coordinates rho phi z, where rho is its distance from z axis, its straight distance from z axis, or you draw a perpendicular on z axis from this point, then length of this perpendicular is rho. You make projection of this segment containing the point and the z axis onto xy plane, right? And that project makes angle phi with x axis, and that phi is, this angle is the second coordinate, right? So this is in cylindrical coordinates. So using chain rule, you can get expression of fx here. So fx is del f by del x, so it can be considered as del f by del r into del r by del x plus del f by del phi into del phi by del x, because x will be considered here a function of r, phi and theta, right? And then del square f by del x square is again partial derivative of fx with respect to x. There also again chain rule can be used. So fx is del f by del rho cos phi minus 1 by rho del f by del phi sin phi, fy del f by del rho sin phi plus 1 by rho del f by del phi cos phi, and we get fz is equal to del f by del z. So Laplacian in cylindrical coordinates therefore is given by this expression. Capital delta is actually nebula square. So this is expression of Laplacian in cylindrical coordinates, and that can be obtained by chain rule. Now the spherical coordinates. The spherical coordinates r theta phi are related to the Cartesian coordinates x, y, z by the relation x equal to r cos theta sin phi, y equal to r sin theta sin phi, z equal to r cos phi, and that is how seen in this figure. So if a point A has its Cartesian coordinates x, y, z, then its r theta phi coordinates, where r is radial coordinate, theta is angular coordinate, and phi is also angular coordinate in spherical system, then r is nothing but we join the point A with the origin or pole, that is 0, 0, 0, and that means the position vector is considered here. So length of the position vector of point A, that gives us the first coordinate, that is the radial coordinate r. Then we consider the projection of point A onto the xy plane. The angle made by this projection with the x-axis in positive direction, that is considered as theta, and the angle made by the position vector of point A with z-axis, that is considered as phi. So this is how r theta phi are connected with xyz, or you can use this relation between xyz and r theta phi coordinates. Now using chain rule again, so partial derivative of f of x, that is now x is function of r theta and phi. So by chain rule, del f by del x can be written as del f by del r into del r by del x. Okay, del r by del x is cos phi sin theta plus del f by del theta cos phi by r minus del f by del phi sin phi r sin theta, and similarly the other first order partial derivatives. So using this, the Laplacian in spherical coordinates is given by nebula square u or delta u is equal to del square u by del r square plus 2 by r del u by del r plus 1 by r square del square u by del phi square plus quad phi by r square into del u by del phi plus 1 by r square sin square phi del square u by del theta square. It is also sometimes written in the form given in the next line. Now this is important. The problem of finding a solution of Laplace's equation that takes on the given boundary values is known as Dirichlet's problem. Such a problem is also called a first boundary value problem of potential theory. Laplace's equation is often referred to as the potential equation. Now we considered a boundary value problem. We are not going to solve these, but just an example of a boundary value problem that is defined by Laplace's equation. So consider the shape of the swap film stretched on approximately horizontal frame. Let z be a function h of x and y be, and that be the description of the shape of this film, that will describe height. Now the tension force acting on the unit piece of the surface is proportional to del square f by del x square plus del square f by del y square, and so del square f by del x square plus del square f by del y square expression equals to 0 for an equilibrium solution. Let h, which is function of x and t, x and y, and x and y depends on time, say t, so ultimately h becomes function of t via x and y.